All right, Chapter 9, Electromagnetic Radiation. Basically what we're learning about is light. So here's the outline. We'll first learn about waves, physics waves, not surfing waves. Then we'll talk about the electromagnetic wave theory of light. We'll discuss the evidence that shows that light is actually a wave. It's not made of particles. We'll talk about force fields again. Then we'll talk about the different types of light. This is called the electromagnetic spectrum, or the light spectrum. Then we'll talk about the sun just for a little bit, the type of light that the sun emits, solar radiation. Then we're going to completely shift gears and talk about ozone depletion. That's connected with the ozone hole in Antarctica. And then global warming, or what we call it nowadays, climate change. So, in this chapter, we continue our study of light. And again, that's very interesting because the correct understanding of light led to both special relativity and quantum mechanics. So here's a reminder. In order to really understand light, we need to learn about waves, electricity and magnetism, and atoms. Well, we discussed electricity and magnetism and atoms in the previous chapter. So now we're going to learn about waves. Okay, when we're talking about waves, we are not referring to large ocean waves that you can use for surfing. So no waves at pipeline. We're talking about nice, repeating, periodic waves, like a sine wave or a cosine wave, if you've ever taken trigonometry in high school. Let me show you a little video. This is a video of a rope wave. Real exciting, huh? All right, so you can see there's this rope, and the person is making it shake up and down. So you can see that there's a wave, or waves. Now, it's kind of interesting. I mean, look at this carefully. You know, you see a pulse, or wave pulse, moving to the right. But look at that. It looks like somebody put a piece of red tape on the rope, or whatever it is. And does that move to the left or to the right? It doesn't at all. In fact, the red piece of rope, it just moves up and down. And that's important. All right. That's not good enough for that. I don't want to see that. Why?
Sound is a wave that we perceive with our ears. It makes our favorite music and it keeps us out of danger, but it's so much more than that.
There are two main types of waves. They're called transverse and
Hey everybody, thanks for checking out D-News today. I'm Trace. Now listen up. Sound is extremely powerful. It's made of invisible waves of energy passing through substances, ground, water, air, particle to particle. The human ear can perceive these waves as long as their frequency is between 20 Hertz and 20,000 Hertz. Anything above or below that we can't hear, but they're still there, because these waves contain energy. And with enough din, you can make these waves do some incredible things. Outside of medical technology like ultrasound, one of the most commonly known ways to make sound do something is by breaking a glass. This works only when the sound wave is at the exact same frequency as the object you're shooting at. If you gently flick a wine glass with your fingernail, you will hear its frequency. Match that tone and turn the volume up, way up to like 11, and that glass will probably break. Also within the range of hearing is sound levitation. This is way cooler than breaking stuff, if you ask me. Sound levitation has been around for years, but until recently, we couldn't do much with the stuff once it was levitated. It just hung there in the air. Thanks to advances at a Swiss university called ETH Zurich, we can not only levitate stuff, but we can move it around, adjusting floating fluids. This works by using the energy in the sound waves. In this apparatus, the energy waves reflect back and forth so quickly they form what's called a standing wave, or a specific point where the energy from the sound can hold an object in midair. Think of it like these silly executive desk toys. The ball in the middle, that's the standing wave.
Is a sound wave.
The thing that they just figured out is how to move the stuff once it's levitating. Now they can use this system to manipulate liquids, combining and separating them, all without touching them with human hands, which is immediately applicable to drug manufacturing. That's kind of cool. These energy waves can do a lot of other stuff too. The LRAD, or long-range acoustical device, is a weapon that shoots sound. It's like a sonic death ray without the death part. It can produce so much sound that you feel physical pain, like 160 decibels. That's loud. Think NASA rocket launch. But it won't kill you. It just really hurts, like a sonic hurt ray. If you combine some of those technologies, sound can produce really strange effects. In the 1950s, NASA and the US Navy built a device that produces ultra-low frequencies, or ultrasonic sound. If you pointed it at a person and set it to 19 hertz, people would have vision problems and get spots and stuff, because 19 hertz is the resonant frequency of the human eyeball. Kind of like that.
That moves all the way from the left to the right, and then from the right to the left. Okay? Now, let's say we had a piece of rope, and you held one end of the rope, and I started shaking the other end. What would you feel? Well, obviously, you would feel vibrations. Now, work is required to produce vibrations, and work requires energy. So we can conclude that energy is being transported along the rope. Okay? And as I said a minute ago, what else is being transported between the ends of the rope? The shape, or the pulse, or the disturbance. Usually we call it a wave pulse, but we can also call it a disturbance. So I think now we've talked about a wave enough, we can actually write down a definition. So here's the definition. Oh, sorry, I got to show you the videos. So let me show you a video of a transverse wave. There we go. So there you go. That's a transverse wave. And let me get out of here. And let me show you a video of a longitudinal wave. Come on.
Meeting in my office at 11, okay?
But we just came from a meeting.
Yeah.
There's a nice longitudinal wave. All right. All right, let's go back to the definition now. So here's the definition of a wave. A wave is a disturbance that travels through an elastic medium and transports energy and momentum. All right, so let's kind of dissect this. First of all, a wave is a disturbance. All right, it has to travel through something. So we saw the waves going through the spring. So the medium was the spring. The medium has to be somewhat elastic because, I mean, you know, it's being disturbed. It has to move a little bit. So that's why we have elastic medium. And again, the wave transports energy and momentum. All right, so I have some silly questions for you. What is the, okay, we drop a pebble in a fish tank full of water. Water waves are created. What's the medium? Water. Very good. All right. I have a rope tied to a doorknob. I start wiggling one end, and I see a wave being produced. What's the medium for the rope wave? The rope. All right, now here's a little bit trickier one. What's the medium for sound wave? It's air. And I hinted at that when I talked about a speaker. So if you went to the moon and you tried to talk, excuse me, it wouldn't work very well, because there's no air there, so you couldn't produce a sound wave. All right. Now, waves are very, very different from particles. So I'm going to call a rock or a marker or something like that a particle. All right? So what I'm saying is that waves are very different from particles. Particles are localized. You can say exactly where you can refer to their exact location. The particle is right there. The rock is right there. Well, you know, waves are not localized. They're spread out. You can't say that the wave exists at one particular point. It's spread out. Particles have mass, right? A rock has mass. But yet, what's the mass of a wave? It doesn't even make sense. Because, I mean, a wave is a disturbance of something, so how can that have mass, you know? So what I'm trying to say, and I'm going to say it again and again, and there's a reason for it, which you'll understand later on, waves and particles are completely different. I'll say it again. Waves and particles are completely different. All right. Now, we want to be able to describe a wave, so there are some terms we need to learn. Here we go. So here's a nice wave. Nice periodic repeatable wave. All right. The maximum is called a crest. The minimum is called a trough. Sometimes I just call it max and min because I'm lazy. But if you want, you can call it a crest and a trough. The distance between adjacent crests or adjacent troughs is called the wavelength. And that's a little Greek letter, lambda. They always use that for wavelength. I don't know why, but that's what they do. The amplitude of a wave is the distance from the center line to the max, or the center line to the min, you know, doesn't matter. So you would just say that the amplitude is A. You wouldn't say it's minus A. You would just say the amplitude of this wave is A, all right? You wouldn't say 2A, the amplitude is A. Okay. If we're talking about a string, a wave on a string, the wave speed, it only depends on the medium, specifically the density of the string and the tension, how tight the string is being held. That's only for a string, the wave speed on a string. Okay, another term we need to know, because we'll use it a lot, is frequency. Frequency is just the number of vibrations in a second. So if you had a rope wave again, how many times you bring that end up and down every single second? That's the frequency. So now I want to show you a little something. All right, let's see. No damping, tension high, no end. All right, so I'm going to show you the difference between a high frequency wave and a low frequency wave. All right, so here's a low frequency wave. So I'm not going to wiggle it up and down very quickly. All right, that's a low frequency wave. I'm not shaking it very quickly, am I? All right, so that's a low frequency wave. Here's a high frequency wave. Okay, it's a high frequency wave. I'm shaking it many times per, well, I'm shaking it more than the other. All right, now let's look at the frequency versus the wavelength. So here's a low frequency wave. So what do you say about the wavelength? Kind of long, right? Kind of long. All right, now I'm going to make a high frequency wave. Not too high because it's hard to see, but all right. Now what do you say about the wavelength? Short, right? Short, right? Okay, so high frequency, short wavelength. Small frequency, long wavelength. Now, just pretend you're holding the end of this, whatever this crazy thing is. Let's say you're out here by the window and you're holding the end. Which frequency will transfer the greatest amount of energy? Do you think this is going to transfer a lot of energy? Do you think it's going to be hard to hold on to this thing with a low frequency? Nah, piece of cake, right? How about this though? Right? A lot of energy being transferred. It's going to be really, really hard to hold on, isn't it? All right? So let's summarize. Let's summarize. So what we just saw is that if you have a short wavelength, 1 divided by something really, really small is big, so you get a large frequency. If you have a long wavelength, 1 divided by something large is small, so you have a small frequency. Okay? So frequency is inversely proportional to wavelength. We're going to use this. Okay, we also saw that energy is proportional to frequency. High frequency, high energy. Low frequency, low energy. Right? Okay, here's a question. I'll give you a minute. Get ready to vote. All right, let's vote. Oops. There we go. All right, so number 1, a row of falling dominoes. Each domino knocks over its neighbor. So you don't see a domino, starting from the very beginning and moving all the way to the end of the row of dominoes, right? You just see the pulse, all right? The pulse moving from the beginning to the end. How about the ripples of the pond? Again, you drop a pebble, you see the ripples moving. You don't see a big hunk of water, where the pebble hit, all of a sudden moving out. It's just the disturbance or the wave pulse moves away from the pebble. All right, here's another one. Get ready. All right, let's vote. Okay, the bottom one has a higher frequency. And how do you know that? Well, because the wavelengths are small. Small wavelength means high frequency. And again, high frequency means high energy. So that's why the bottom one has small wavelength, high frequency, high energy. Okay. All right. Now we're going to talk about something that waves exhibit, particles do not. This is called wave interference. So let's talk about radio waves. How many radio waves do you think are going through this room right now? Well, I hope you're thinking lots. Well, how do you know? I mean, how could you determine if there's lots of radio waves? Pretty simple, right? If you had a whole bunch of radios, just turn them to different stations or different frequencies, and voila, you would be able to determine, yeah, there's lots of radio waves because I can hear lots and lots of different stations. Now, all right, so let's just say there's lots of radio waves going through this room. What do these radio waves do? I mean, do they just pass through one another, or do they collide and make a bunch of noise? Well, once again, if we had a bunch of radios in this room and everybody had a pair of headphones listening to the radio, I think everybody could hear the nice music from every single station, right? I mean, you wouldn't hear these radio waves colliding, making noise. I mean, you would be able to hear every single station very nice and very clearly. So what does that imply? I mean, what I'm saying is you could hear every station by itself. So what does that imply? It implies that the radio waves just pass through each other. They don't collide and reflect and make all this mess, noise or whatnot. They just pass by each other. They pass through each other. So let's talk about that some more. This ability to pass through each other. We'll start off with one-dimensional waves. Keep it easy. So here's a one-dimensional wave. Just moves in one dimension, right? So look where it says the before. So we have a pulse with large amplitude moving to the right. We have a pulse with small amplitude, negative, moving to the left. You can see that they interfere. So it kind of looks like, a big hump with a little hump, right? But then after that interference where it says during, what do you notice? The large amplitude wave that was moving to the right is still a large amplitude wave moving to the right. The small negative amplitude wave moving to the left is still a small negative amplitude wave moving to the left. So what happens? They're just passing through one another, That's all. Here's another one. So now the wave pulses have the same shape, except one is positive, one is negative. You can see one's moving to the right, one's moving to the left. So when they interfere, what does it look like? It looks like they disappeared, right? But did they really disappear? No, because, the after shows that the one that's moving to the right just keeps moving to the right. The other one keeps moving to the left. That's all there is to it. Okay, one more. Now we have same shape pulses moving toward one another, both positive amplitude. When they interfere, what does it look like? It looks like it doubled, right? The pulse has doubled in amplitude. But after that interference, what do you notice? They just move along their merry way like nothing happened at all. So what am I trying to say? Waves just pass through one another. All right? They appear to cancel or add or something at one point, but really they're just passing through one another. Now, does this happen to particles? Of course not. Have you ever thrown a rock at another rock and seen them pass through one another? That'd be very interesting. All right. So here's a nice slide. I'll show you this a couple times today. Particles versus waves. So on the left, we have two pitching machines. They throw their baseballs at the same place at the same time. Do they go through each other? No, they don't go through each other. They just bounce off one another. So as it says in blue on the bottom, the balls collide and bounce apart. Two particles cannot occupy the same point of space at the same time. On the right, we have two loudspeakers. What do you notice? The waves pass through one another. The sound is beautiful no matter where you are. So the waves pass through each other. So unlike particles, in the red, unlike particles, two waves can pass directly through each other. All right, now there's some special types of this interference that we're talking about. So let's go over these special cases. So this is called constructive interference. So you notice that the max of the blue is at the same location as the max of the yellow wave. The mins are the same. The wavelengths are the same. So, we would say these waves are in phase. You don't have to know that term, but they're in phase. So when they add, what's it going to look like? Well, obviously, we already saw this. The max here will add to the max here, and bingo, right? The maxes add, the mins add, everything adds. So you get a wave that has twice the amplitude. So that's called constructive interference. Okay, let's do the other one. Destructive interference. Now the waves are out of phase. You have the max at the blue, same place as the min of the yellow. You have the min of the blue, same place as the max of the yellow. What's it gonna look like? Well, if you have a max and a min, what's gonna happen? It's gonna look like it cancels, right? So we're gonna have cancellation. So bingo, that you get just cancellation. So that's destructive. Complete canceling. So this is complete adding, constructive. This is complete canceling, destructive. So here's a question for you. Get ready to vote. Now notice it's really two questions here. Notice also that the picture does not correspond with the text. The text clearly says identical shapes and heights, which is completely not what the picture shows, but that's okay. All right, let's vote. Let's do the first one. All right. The first one is if one is up and one's down, what are we going to see? Just destructive interference, just like we just discussed. How about if both are upward? We'll have constructive interference, just like we just discussed. All right. So this is one-dimensional wave interference. Now we're going to get a little bit tougher and talk about two-dimensional wave interference. What's a two-dimensional wave? Well, you have a fish tank full of water. Yeah, drop a little pebble in the water. What's it going to produce? It's going to produce a circular wave. That's a two-dimensional figure, right? It's not a straight line. It's a two-dimensional figure. Okay, so here we go. So here you can see you have two circular waves being produced by someone dropping drops of water at two different locations. And you see the nice circular waves, but look where you have this wave interaction region. What's going on there? It looks kind of complicated, doesn't it? Something's going on, you know? So that's the interaction where the waves are interfering. This picture was made from, okay, you have a pan of water. Let's say you have a rectangular pan of water, and you have these two hammers. These little things that come down on the left, they just hit the water, okay? It's called a hammer. It doesn't look like a hammer, but just who cares? So they're just hitting the water. And so each hammer is making a circular wave, and then you can see that there's some patterns going on, right? There's some patterns going on. So what we want to do is, I mean, some places it looks like the water's moving up and down a lot. Some places it looks like the water's not moving at all. So we should be able to explain that, and we will. All right, so this picture here is incredibly important. You must understand it, right? It's that important. Okay, let's talk about the line made with the X's. Let's start out here. Okay, well, let me back up. Sorry. This here is a max or a crest. This is another max or a crest. So these solid black lines are the crests of the waves produced by the hammer at point A. So what's the distance from this crest or black line to this crest or black line? Wavelength, right? Because a wavelength is the distance from one crest to another. So for the distance between adjacent black lines is one wavelength. All right, let's go back over here to the right. So at this X, what is this from, okay, regarding hammer A, what is this? A max? Come on, where'd you go? Right here. Is this a max or a min or none of the above? Well, you can see it's a black line, so it's a max. It's a crest, right? Now consider hammer B. What is this position here from, with regards to hammer B? Well, hammer B, we're denoting the crests or the maxes with a blue dotted line, right? So here you go, right here. It's a max, right? It's a blue dotted line, so it's a max. So we have a max from hammer A. We have a max from hammer B. What do you do if you get a max and a max? You get constructive interference. So what's the water going to be doing? Right at this point, it's going to be moving up really high, right? Double the amplitude. Okay? Let's go here. What is this in regards to hammer A? Well, it's between two maxes. So what's between two maxes? A min, a trough. What is it in regards to hammer B? Well, again, it's between two maxes, so it's a trough. So it's a trough from A, it's a trough from B. What do you get when you get two troughs? A super trough. Just kidding, right? You get, again, it's constructive interference, but now it has a large amplitude in the negative direction. Okay, what's this? Two maxes. What's this? Two mins. Two maxes, two mins, two maxes, two mins. So basically, along the line with the X's, what's the water doing? It's moving up and down like crazy, right? Sometimes it's moving up, sometimes it's moving down, but it's shaking like crazy. All right, let's go to the line with the zeros. All right, right here, what is that with regards to hammer A? Well, it's a black line, so it's a max. What is this with regards to hammer B? Well, it's between two blues, two dotted blue lines, so it's a min. So you have a max from A and a min from B. What is a max and a min? Cancel each other, right? So the water doesn't move. All right, how about this one? It's a max from hammer B. It's a min from hammer A. Max, min, destructive interference. The water doesn't move. All right, how about here? Max from A, min from B, destructive. Here, max from B, min from A, destructive. So basically, everywhere along the line with the zeros, you're going to get destructive interference. So what's the water going to do? Nothing. It's not going to move at all. All right? So the line with the X's, the water's shaking around like crazy. The line with the zeros, the water is not moving at all, and so forth and so on. Now, again, let's say that this here, the water is in a pan, and then on the right, this is the end of the pan, and then on the right, I have XO, 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 and so forth. So here, I'm outside of the pan. So if I'm looking at the water in the pan and I'm at an X point, what am I going to see? I'm going to see the water going up and down like crazy, right? What am I going to see at the O? Nothing. Well, the water's not going to be moving at all. It's going to be still. Then at the next X, water's moving like crazy. Then at the O, water's not moving at all, and so forth and so on. So the point is, when I have these two hammers or two sources of waves, sometimes I get constructive interference, sometimes I get destructive interference. But I see a pattern, right? Constructive, destructive, constructive, destructive, constructive, destructive. So I see this interference pattern with two sources of waves. Now, look at here. So here, hammer B is not operating at all. Hammer A is making circular waves. So do you see any kind of interference pattern? No. So if I were at the right, outside the pan of water, looking at the water, what would I see? I see everything, right? I'd see it, not moving, then moving a little, moving more and more and more and more, then maximum height, then smaller, 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 not moving at all, then down to the negative. I just see everything, right? So with one source of waves, I see the water going to every single height, no matter where I'm standing or looking, But, But with two sources of light, depending on where I am, I see the water moving, not moving, moving, not moving, all right? So you need the two sources to see the interference pattern. With one source, no interference, like I say up here. All right. So, does this happen with particles? No. We don't get any kind of interference pattern with particles. So once again, I'm going to show you this slide. It should be really simple to distinguish between a particle and a wave, right? Waves, if you have two or more sources, they're going to have an interference pattern. Particles, I don't care how many particles, you're not going to see an interference pattern. Waves move through each other. Particles do not move through each other. Okay? Here we go. Here's the question. Oh, I don't want to watch that. Okay, sorry. Hold it. Now, remember we're supposed to be learning about light. So the question that the 1800 and other time frame physicists had is, what's light? Is it made up of little tiny particles? Or is it a wave? Now, how do you see something? Look at your pencil or your pen. How do you see that? Well, the light from the sun or the light from the light bulb in this room or something reflects off of your pen or pencil, and then the light reflects into your eye. If this room were completely dark, could you see your pen? No. All right. Without reflection, we wouldn't see anything. Think of a black hole. Remember we talked about black holes some time ago. Nothing can escape a black hole, not even light. So that means that light can't reflect from a black hole. So we can't see a black hole. It's black. All right. Now, again, a physicist a long time ago had this question: what's light? Is it a bunch of particles or is it a wave? Now, at the time, the technology was not terrific, and so when physicists did experiments with light, they could not see any kind of interference effects. So people said, okay, no interference, so it's a particle, right? Everybody said waves made up of tiny, tiny particles. In fact, Isaac Newton, the famous physicist who did so many wonderful things, he agreed. He said light is made up of particles. So, you had the data that indicated light's made out of particles, and you had a person of the stature of Newton who said light's made out of particles. So pretty much everybody said, okay, light's a particle, or light is made up of many, many particles. But in science, it's always good to have people who think a little bit differently. That's how you make progress. And so there were some people who disagreed with that. So right now, Nate is going to do a little demonstration for you. So he's going to take a laser pointer, and he's going to shine it through a slit. Now let me back up. So he has a piece of glass. There's black paper on each side of the glass, but there's little slits in the black paper. So first he's going to shine the laser pointer through a single slit. Okay? Now, if light's made out of particles, and you're shooting all these little particles through a slit or like a hole, or what do you want, something like that, what are you going to see? Well, you're going to see a hole, or a slit will be, right? Not a big deal there, So the next thing he's going to do is he's going to shine the light through two slits. Now these slits are very close to one another. So basically what's going to happen is you're going to have like two sources of light. Now, think carefully. If light's made up of little tiny particles, when you shine the light through the slits, and the light hits the wall, what are you going to see? You're going to see two bunches of particles, right? You can see two bright spots. That's all. Just two bright spots from the particles of light going through the slits. On the other hand, if light is a wave, this is just like having two sources of waves or two hammers in the water, and you're going to see an interference pattern. Okay, Nate, do it. All right, so when Nate shines the laser pointer through the two slits, you don't just see two bright lines or two bright spots. You see an interference pattern. So what does that mean? There's only one explanation. Light acts like a wave. Light is a wave. All right? Pretty interesting. Something else that's kind of neat about this experiment, the maximum intensity of light, along the wall, if you could work out all the details, you would notice that the maximum intensity happens between the two slits. Well, come on, between the two slits there's no light going through. How can you get the brightest spot where there's no light going through? The only way to explain it is interference effects, okay? So what I'm saying is that someone actually did this experiment. It wasn't easy like here because they didn't have lasers, Lasers are nice because all of the waves are in phase. So they all come to the max at the same time. They all come to the min at the same time. The person who actually did this experiment, again, lasers hadn't been invented, so he had to figure out a real clever way to do it with just regular light. But he did it, and he showed that light acts like a wave. And as soon as he did that experiment and was able to repeat it, everybody basically said, okay, Newton's wrong. We're all wrong. Light is a wave. Because there's no other way to explain it. All right, there's another demonstration that shows that light is a wave, and you can do it. In fact, I'd like you to do it right now. So what I'd like you to do is look toward the light in this ceiling, and then take your hand and take your index finger and your thumb and put them together, and now bring them apart. So get them as close as possible to one another, but have them not touching, right? And then look through that little distance at the light, all right? So you're looking at the light through your index finger and your thumb. And again, you want your thumb and index finger to be as close as possible, but no touching. What do you see? You see a little pattern, don't you? You see a pattern. That's actually an interference pattern, okay? So that's pretty neat. All right, let's go back to the definition of a wave. Waves transport energy. Now, we just said that light's a wave. Does light transport energy? Well, who here has ever gotten a sunburn? So I assume most of the hands are up. Where did that energy come from? The sun. That's why it's called a sunburn. The sun is 93 million miles away. How did that energy get from the sun to your skin? Well, through a light wave, right? So light does transport energy. Let's go back to the definition again. A wave is a disturbance of a medium. All right. Well, if light's a wave, what's the medium? Now remember, light travels through deep outer space. And deep outer space is basically empty space. There's almost, let's just say there's no air there, all right? Close enough. Well, if there's no air out there, but yet light is traveling through it, what's the medium? Well, apparently it's not a material, right? It's not made out of atoms, so what is it? Well, I want you to think back now from a previous chapter. What exists everywhere? Fields, right? Electric fields, magnetic fields. So believe it or not, electromagnetic fields, which we've discussed, these electromagnetic fields, that's the medium for light. We're going to discuss that more in a couple of minutes, don't worry. Now this was amazing to the physicists at the time because every type of wave that they had ever learned about or discovered or played with, the medium was always something you could touch. It was always made out of atoms. I mean, a water wave, a rope wave, sound wave. I mean, it was always, we would call those, the medium was material made out of atoms. But here you have a medium, electromagnetic fields, no atoms. So that was very difficult to grasp conceptually for the physicists at the time. All right, let's talk about this whole idea of light. We're going to call it the electromagnetic theory of light. Okay, in the 1860s, there was a physicist named James Clerk Maxwell in England. He combined all the experimental information about electricity and magnetism into a set of equations. What I'm saying is he became familiar with all the experimental data about electricity and magnetism. And he decided that he would write the mathematical theory of electricity and magnetism. And as I've mentioned in the past, that's really important to have a mathematical theory, because you can use it to make predictions which can therefore be tested. So the people who write the mathematical theory, they always get a lot of credit, and they deserve it. All right, so Maxwell wrote this mathematical theory of electricity and magnetism. His theory included 20 equations. Now, thankfully, there were some other brilliant people around at the time, and they realized that they could combine some of these equations. So they spent years combining these equations, and they finally came up with 4. So these are called Maxwell's equations. Do not concern yourself with the math, please. All right. I mean, we're going to talk about them, but you're not required to understand the math. Okay. What's important, I mean, there's lots of things important, but one very important characteristic of these equations is that they are in terms of fields, not particles. You see the uppercase E and the uppercase B? E stands for electric field. B stands for magnetic field. So all of these equations have E's and B's. So what I'm saying is, these equations, which pretty much describe everything about classical electricity and magnetism. I say classical because they don't work for quantum mechanics. So these equations, they work, all right? They work for classical electricity and magnetism. And they're not in terms of particles. They're in terms of these fields, which aren't even material, all right? So that's amazing. Now, let's go through these equations. First one, don't worry about the math. The first one just basically says that charged particles produce electric fields. That's what it says. The second one says that there's no such thing as a magnetic monopole. We already learned that, you know. It also says that when you have moving charged particles, you get magnetism, magnetic fields. All right, the third and fourth one, we're going to talk about these in quite a bit of detail. The third one says if you change the magnetic field, that's the dB over the dt. The t is time, b is magnetic field. The little curly thing is the derivative. Don't worry about it if you don't know what I'm talking about. So this is, if you change the magnetic field, you produce an electric field. The fourth one, and again, we saw that already. When I move the magnet through a coil of wire, I produced a current, right? So I changed the magnetic field and I produced electricity. The last one, the fourth one, says when we change the electric field, that's that little dE over dt, when I change the electric field, I produce magnetism. And that's just basically a current through a wire produces a magnetic field. All right. Now, again, we want to talk about these last two because they're important. You'll see why. So here we go. The last two. All right. So this one here, the first one, again, it says if you change the magnetic field, you produce electricity. This one says, the second one says, if you change the electric field, you produce magnetism. Okay? You got to know that. All right. Now, let's use this, see what we come up with. All right, here we have a comb. Let's say that we're living in the desert of Arizona, so it's real dry. So we comb our hair and we get the comb charged, electrically charged, just like the hair becomes electrically charged, okay? So all right, so we have this charged comb. So right away we know if you have something that's charged, you produce electricity, right? All right. But we're not going to just hold on to it. We're going to wiggle it. Okay? So we're going to create a changing electric field. Now, what did we just learn from Maxwell? If we have a changing electric field, we create a magnetic field. Right? Now, generally, this magnetic field will be changing. And what did Maxwell tell us? If we have a changing magnetic field, we'll get an electric field. And again, generally, that electric field will be changing. So it's going to be creating a changing magnetic field, and so forth and so forth. So here we go. So again, just to repeat, a changing electric field creates a changing magnetic field, Changing magnetic field creates a changing electric field. That's what we have. That's what's going on when we wiggle our charged comb, okay? And according to Maxwell, what do we get? Changing E, which is electric field, creates changing B, magnetic field. That creates changing E, that creates changing B, that creates changing E. All right, I'm tired of it. All right, you see what's going on? So what's going on here? Well, look, as soon as we have a changing field of either E or B, what happens? We get a self-perpetuating system of E and B fields, right? In other words, you can take away the comb, right? As long as you get this thing going with the comb, then you take away the comb, and you don't even need it anymore, because the changing E field produced by the comb is going to produce a changing B field, which is going to produce a changing E field, and on and on and on. So it's just going to keep on going, right? You need a comb to start it, but then you can just throw it away, okay? So once these fields get started, they take on an independent existence. They're no longer associated with the charged comb, you know? Now, Maxwell used his equations, and he thought about it, and he said, golly, you know, you're having these electric fields and magnetic fields are propagating through space, right? As a wave, you know? Really, these fields are propagating through space as a wave. So he called it an electromagnetic wave. Sounds kind of logical, right? Electric and magnetic, you know? So he said it's an electromagnetic wave. And like all waves, this wave carries energy, but certainly not matter. Okay, so he used his equations to calculate the speed of the wave. Again, don't worry about the math. I mean, if you know it, then it's awesome, but if you don't worry about it. The equation top left is it's called the wave equation. And that little v is the velocity of the wave. This is what Maxwell had. So this in yellow has to be the speed of the wave. So like I show here on the second line, 1 over the speed of the wave equals this square root thing. These are just constants of nature. Everybody knew what they were, you know. So Maxwell just calculated it. And lo and behold, the answer was 300,000 kilometers per second. Now, so basically he came up with this. He said, look, the only way you're going to get this self-perpetuating structure of electric and magnetic fields is if this wave travels at this particular speed. No other speed would work, all right? No other speed satisfies Maxwell's equations. Now, what's so special about 300,000 kilometers per second? The speed of light. All right, it's the speed of light. And people back then knew it. So what did Maxwell reason? Well, you have this wave. You know, you're disturbing these electric and magnetic fields, and you have this wave, and it's moving at the speed of light. So what did you just discover, basically? You just discovered light. I mean, right? I mean, if a duck looks like a duck, quacks like a duck, smells like a duck, it's probably a duck, right? Well, if you have this wave that's moving at the speed of light, what is it? It's light. Okay? So Maxwell reasoned that light is a disturbance of an electromagnetic field. So that was his prediction that he came up with just by using his theory, his mathematical equations. Now, of course, this is physics. You know, just because it's beautiful mathematically doesn't mean anything. You have to have data. So about 20 years later, there was a guy named Hertz from Germany. He was able to wiggle some charged particles in his lab. The details are in the book. So he was able to accelerate or wiggle some charged particles in his lab. They created waves. He was able to measure the speed of the waves. And guess what? 300,000 kilometers per second, speed of light. So Hertz, by wiggling charged particles, he produced electromagnetic waves that travel at the speed of light. So he basically verified Maxwell's prediction. The sad part about it was Maxwell died when he was very young. He did not live to see this data. He didn't live to see the experiment that Hertz produced. Kind of sad. All right. Okay. So let's review. So if light is a wave, what's the medium? Electromagnetic fields that are not material, right? They're not made out of atoms. Okay. Here, this is right out of the book. This is called the electromagnetic wave theory of light. Every vibrating or accelerating charged object creates a disturbance in its own electromagnetic field. That's a wave, right? A wave. A disturbance of a medium is a wave. This wave spreads outward through the field at 300,000 kilometers per second. Light is such an electromagnetic wave. Now, if you want to be a real physics nerd, certain things you have to do. One is you have to buy a t-shirt. Here's the typical physics nerd t-shirt. I'm proud to say I never bought one, but a student gave me one, so what can I say? All right, so here you see, it says, and God said, and then you see the four Maxwell equations, written a little differently, but don't worry about it. They're the four Maxwell equations. And then at the bottom it says, and there was light. Okay? Because Maxwell's equations, they basically explain, they predict and they explain light. Okay? So there you go. You can buy on these on the web, by the way. Okay, here's a question for you. Get ready to vote. I'll give you a little time. All right, let's vote. Okay, let's go through it. Okay, you have a charged comb. You're shaking it. What happens when you get a charged object shaking? You produce an electromagnetic wave. All right. So number 1 and number 2 are wrong because you don't get a sound wave. You get an electromagnetic wave. Okay. All right. So now it's between 3 and 4. Now, let's see. You're shaking it back and forth at a frequency of 1 hertz. Well, what's the frequency of the light wave going to have? 1 hertz. All right. Now it's light. What's the speed going to be? Speed of light. So that's why answer number 4 is correct. You shake the charged object, so you get an electromagnetic wave. Your frequency is 1 hertz, so the light wave has a frequency of 1 hertz. It's light, so it travels at the only speed light can travel, which is 300,000 kilometers per second. Now, Maxwell also predicted that these electromagnetic waves, or light waves, can have any frequency. Therefore, they can have any energy in any wavelength. So this is something you'll see in pretty much every physics book. This is called the electromagnetic spectrum, or you can call it a light spectrum. It just, when you talk about the word spectrum, it's just basically dividing up the light into the different wavelengths or different frequencies. So you can see on the horizontal lines, the bottom one says wavelength. Look at the range, unbelievable. On the left, 10 to the minus 16 meters. On the right, 10 to the 6th meters. Amazing, right? I mean, 10 to the minus 16 is smaller than a nucleus. 10 to the 6th is bigger than a mountain. So, there's quite a range for the wavelengths of the different types of light. Look at the frequency. On the left, 10 to the 24. 10 to the 24. Can you imagine doing that? Try to shake something 10 to the 24th times a second. Good luck. On the right, 10 to the 200. I mean, that's still kind of crazy, right? Try shaking something 100 times a second. But all I'm saying is look at the range. 10 to the 2, 100, all the way to 10 to the 24. Unbelievable, right? Okay, let's talk about the different types of light. I'll start at the left. So gamma rays. So, like gamma rays have high frequency, small wavelengths. What kind of energy? High energy, right? High energy. And what are gamma rays used for in a hospital? Kill cancer cells. All right, let's keep going. Move to the right. Then we have X-rays. Hard and soft X-rays. Now, you know as well as I do that X-rays are dangerous, right? When you go to the dentist to have X-rays taken, what do? They put this lead apron on you to protect you. All right, because once again, high frequency, small wavelength. So there's a lot of energy in the X-rays. Keep moving. UV. Ultraviolet. UV. Ultraviolet light causes skin cancer, damages DNA. All right? It's not as energetic as X-rays and gamma rays, but still, it's harmful, And you can see the size, right? UV light, like virus or something like that. Then we have this little region here, visible light. Think about it. The whole spectrum of light, visible light is only a tiny, tiny fraction, right? Okay, so visible light, you can see the wavelength 4,000 to 7,500 angstroms. Not a big difference, you know. I mean, really, it's not a big difference. Not a big difference in the frequency. Different colors. So for visible light, different color means different wavelength, or you can say different frequency, or you can say different energy. But again, it's only this little slit here, you know, that's visible light. So again, visible light doesn't make up much of the spectrum, does it? Okay, let's keep going to the right. Infrared, right, and then radio. Look at the wide range for radio. Some radio waves can be the size of a pin. Some can be the size of a mountain. Good golly, you know. All right. Yeah, let's go back. Okay, so let's say you're an astronomer and you're looking at a star or a galaxy or something like that. So let's say you only have a visible light telescope. Well, come on. Look at this spectrum. If you only have a visible light telescope, you're only getting the information for this little narrow range of visible light. You're not getting any information about the gamma rays that the galaxy is producing, the X-rays, the UV, the infrared, the radio. So are you really getting are you getting the full story? No. You're getting just a little tiny fraction of it, you know. So here, this is really kind of neat. So bottom right, this is a star chart, okay? And you can see the map, right? The chart of the stars. Okay, very nice. All right, bottom left, you see a little V here? That means visible. So this photograph was taken with a visible light telescope that, you know, that most people have access to, right? Like universities and all that. And so this is what it would look like if you had a nice telescope looking at the night sky. Very nice. Top left. See the little U here? That means UV, ultraviolet light. So this picture was taken with a camera that's only sensitive to ultraviolet light. Now think about it. If you're used to seeing this picture bottom left with a visible light telescope, and then somebody shows you this UV picture, what's your reaction? You go, wow, what's going on here? There's all this new stuff, you know? I mean, you'd be really excited. Okay, top right. See the eye? That's infrared. My goodness, look at all that stuff that you had no clue about if you were looking at only visible light. So again, if you're an astronomer, you say, man, there's tons of neat stuff I got to learn about. All right? So all I'm saying is that, you know, in the olden days when we only had visible light telescopes, we weren't seeing the whole picture, you know? So nowadays, we can pretty much cover almost the entire spectrum. We have radio telescopes, we have infrared telescopes or cameras, we have X-ray cameras, gamma ray telescopes, cameras, all sorts of things, you know, satellites. So now we're learning a whole lot more than people even dreamed of before. It's really amazing. Well, let me get back. Infrared light. You might be interested to know that everything that's above absolute zero in temperature produces infrared light. You know, the molecules are vibrating and they produce light, infrared light. So we actually produce infrared light. If we had an infrared camera, we could see each other in the dark. So if I turn off the lights in this room, covered all the windows and everything, if I had an infrared camera, we could see each other. And you know, like firefighters use these things when they enter buildings. Military use infrared scopes to see the enemy in the dark and so forth and so on. So anyway. All right. Here's a picture of a person who's very ill. This is made from a computer, okay? So we call it a false color image. It's infrared light, of course, which we can't see, you know. But the computer, what it does, the computer measures every color represents a different temperature, all right? So the right side of this person is sort of normal, but the left side, there's something really, really wrong, you know. When you see all those yellows and reds and whites, that means that the temperature is not as it should be, okay? Here's a good BYU picture, right? So once again, the colors represent temperature. The white and the yellow are regions of high temperature, okay? Again, this is a false color thing where the computer, you know, has the temperature and converts it to color so we can see it. All right, here's some questions for you. Now these are kind of tough question, so be careful. All right, let's vote. Okay. Hertz's waves had a frequency of 10 to the 10th hertz. Oh yeah, there's another unit, right? The unit of frequency is hertz, named after guess who, right? All right. So 10 to the 10th. So you go over here, and 10 to the 10th. Where's 10 to the 10th? Is it in radio? Nope. It's in radar, right? 10 to the 10th is in radar. So we could not receive waves of this type and frequency with our radios because it's not a radio wave, it's a radar wave, right? I mean, FM is like 10 to the 8th, 10 to the 9th, AM 10 to the 6th, 10 to the 7th, you know? So 10 to the 10th is radar. Okay, another one. There's really two questions here, so be careful. All right, let's vote. All right, now, let's see. We want FM. So we know we're going to be down here, 10 to the 8th, 10 to the 9th, right? Somewhere in here, right? Now, let's see. Well, first of all, hold it. Okay, what kind of wave does your radio receive? Well, the radio station has an antenna. The antenna produces a radio wave. Radio wave, that's a type of light. Okay, so right away, 1 and 2 are wrong because it's not a sound wave, it's a light wave, electromagnetic wave. All right, so 1 and 2 are wrong. Now, FM is somewhere between like 10 to the 8th or so and 10 to the 9th or so. Okay, let's see. Number 3 says 100, wrong. Number 4 says 10 to the 6th, that would be AM, wrong. Number 5 says 10 to the 8th, okay, maybe. Number 6 says 10 to the 8th, okay, maybe. All right, so it's either going to be 5 or 6, right? Okay. But then we want to know the wavelength. So we put our little cursor or whatnot around 10 to the 8th, 10 to the 9th, go horizontally, straight across. And what do you notice for the wavelength? A frequency of 10 to the 8th or 10 to the 9th has about a 1 meter wavelength, right? So 5 is wrong because it says 100 meters. 100 meters would be like AM radio, right? So number 6 is right because 10 to the 8th FM gives a wavelength of a meter. Make sure you understand this because you're gonna see stuff like this on the tests and in the homework. Okay, another one. This is easy. Come on, let's vote. What comes from the radio? The radio has a speaker. What kind of wave does a speaker produce? A sound wave, right? So the sound that comes from the radio is produced by a speaker. It's not light, it's a sound wave. And as you know, sound travels much, 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 much slower than light. All right. That's a good place to quit. So we'll see you Wednesday.